Thank you very much. So first, let me thank the organizers for the kind invitation. I'm very happy to be here today. So this is a joint project that I carried out with two colleagues of mine, Monica Conti and Claudio Giorgi, and my former PhD students, Valeria Danesi. The starting point of this work is this equation here that I denote by V. And this is the equation of linear viscoelasticity, which rules the evolution of the axial displacement, denoted by U, of a linear homogeneous viscoelastic body. And we assume that the body occupies a volume let's say smooth bounded volume of R3, or more generally of Rn. You see this equation has a first, let's say, component, which is the wave equation, and then there is this part in which a convolution integral appears, and this part confers the equation in a local character. And then here we assume, for simplicity, but you can do also, I mean, you can act differently. We assume Dirichlet, homogeneous Dirichlet boundary condition. The important thing is this function G. This is the convolution kernel, which is usually it is referred to as the memory kernel. This is non-negative convex summable function. And the interesting feature of this equation is that you see these integrals goes from 0 to plus infinity, meaning that, assuming that you give initial data at time t equal to 0, you need to know the values of u up to minus infinity. Namely, you need to know the past history of u. And for this reason, us for s less than or equal to 0, namely the initial past history, is assumed to be a known datum. And in the terminology of Dautrey-Lyons, this is referred to as viscoelasticity with long memory. And what happens instead if you take this kernel G and you let it collapse to a Dirac mass at 0, and then you end up with this equation here that I denote by KV. This is known as the Kelvin-Voigt equation. Sometimes referred to as a strongly damped wave equation, although this terminology is not completely correct, because this is not a wave equation in the sense that it exhibits parabolic features in the velocity. But anyway, this is what is known as viscoelasticity with short memory. Now, a way to, an effective, although simplified way to represent linear viscoelasticity is to use rheological models. Namely, one thinks of the material, each point of the material, which is homogeneous, as a linear combination of springs and dashpots. And so if we apply this method here, we have these two models. The first one is the models from which you deduce the equation of viscoelasticity. And the rheological model here is you have a spring which is in parallel with the Maxwell element. The Maxwell element is a spring in series with a Newtonian dashpot. And what happens in short memory viscoelasticity is that the rheological model is the same, except that you don't have any longer this spring here. Or in other words, you can think that this spring becomes completely rigid. And this is in our opinion, the correct way to understand the collapse of this model to this model here when the kernel becomes the Dirac mass at 0. Now, this goes to the heart of our problem, because what we want to do is to describe a viscoelastic material, assuming that the structural properties of the material might change over time. Now, let us refer to these changes, to this change conventionally. Let us call it aging, okay? So what is the effect of aging? With reference, to the equation of viscoelasticity, aging should, produce a change in the shape of the memory kernel. And so our aim is to find an evolution for the displacement U, accounting for this aging process. But what we require is that this process has to occur within the dynamics. And now I will explain a little bit better what I mean. In which sense we want to depict this aging process? Well, we imagine that the aging process is described by a progressive loss of the elastic response in the Maxwell element. In other words, the spring in the Maxwell element has to stiffen. And the way to describe this fact is to assume that the Hooke constant is not any longer a constant, but it depends on time. And the stiffening of the springs is the same as saying that the Hooke constant goes to is an increasing function, and at the end it goes to plus infinity. Okay, so as I was saying, in mathematical terms, this translates into having a memory kernel depending itself on time. Let me just mention what we did in some previous papers. So there's a pretty old paper, well, old, almost old, say, paper with Monica Conti and Marco Squassina, in which we tried an approach of this kind, replacing the memory kernel with a family of memory kernels G epsilon, with the property that as epsilon goes to 0 plus, G epsilon goes to the Dirac mass at 0 in some distributional sense. And what we studied in that paper was we wanted to investigate the closeness of the epsilon dynamics to the limit 0 dynamics corresponding to the Kelvin-Voigt model. But using this approach, of course, this parameter epsilon is somehow artificial, and for each different epsilon you have a different dynamics. So what we want to do here instead is a different story. We aim to model the aging material which loses memory over time. So this stiffening process has to be built in the dynamic. And we would like to reproduce the singular limit in epsilon as we did in the previous paper, but now this has to be an intrinsic limit. So what we do, let us go back to the Rheological model. And now the change basically is here. We do not consider the Hooke constant of the spring in the Maxwell element as a constant any longer, but a function. We make really very minimal requirements to this function. So one is that to minus infinity has to be greater than 0, and non-decreasing, well, increasing, say. This is the only thing that we know, that we ask. Then if you make all your calculations that I will omit here, and you find the constitutive equation for the stress, what you get is the stress assumes this form, and then when you do the balance of linear momentum, what you get is finally your motion equation. You see this motion equation here is exactly the equation of viscoelasticity. This G infinity is a constant. But the kernel now depends also on T, and it has this explicit form. Of course, what happens when K0 of T is just K0, is just a constant? Well, as we expect, if K0 is, let's say, alpha, constant, then your kernel does not depend any longer on time at an explicit level. And what you get is just the exponential kernel, and the equation is this. So this is the equation of viscoelasticity, where the kernel is the negative exponential. Okay, and as I was saying before, the relevant case is when
I'm sorry. I'm sorry. I think there is a question.
May I ask you a question?
Yes.
So this in this Rheological model you were using before, the K0T is a given that datum. So, yes. Or you don't have an evolution law for that?
It is given. It is given.
Okay, it's given.
Well, it should reflect the, let's say, I'm not really an expert, because the expert for these for the more physical aspects was Claudio Giorgi, but it should be a distinctive character of a particular material under consideration.
So the aging does not depend on the history.
Well, the aging depends on the history, but also on it's a mixture of let's say the structural properties, let's say the predisposition of the material to aging, and which kind of past history you choose.
Okay, thank you.
Okay, so as I was saying, if you consider this relevant, at least from our point of view, this relevant case, then, and this is from my point of view quite remarkable, because you see you have this function here. This function here contains this K0 of T, which is the same that appears here. So this is very general, because as I was saying, this is just an increasing function that goes to infinity. And what you get is that this converges in the distributional sense to a multiple of the Dirac mass at 0. And the multiple is this gamma, which is the same gamma that appears here. And so, at least at the formal level for the moment, what you get is that this equation, which is the equation, let's say, of viscoelasticity with a time-dependent kernel, converges to the equation, to the Kelvin-Voigt equation. And as I was saying, if you take gamma equal to 1, this is an approximation for the Dirac mass, of which I was not aware before. Okay, now these somehow justifies why we are interested in considering an equation of this kind, where now this kernel is a general convex ensemble function for each fixed T, which has to satisfy some suitable assumption, and the Rheological kernel turns out to be a particular case of this more general kernel that we investigate. Again, we take the Dirichlet boundary condition, and we assume also to have a displacement, possibly displacement dependent external source of this form. F of u is cubic. Here you cannot go more than the cubic nonlinearity, and satisfying some, let's say, natural dissipation properties. Okay. Now, as I was saying, one difficulty of an equation of this kind is that it has a non-local character. And so, in fact, there is a way which goes back to a very famous paper of the Fermos, published in the 70s. There is a way to hide this non-locality and produce a dynamical system, if not a semigroup, at least a process acting on a suitable space. And the idea is to introduce an extra variable which usually is called eta. You see that eta depends on t and on s. T is the actual time. S, basically, since it comes it comes into the picture with this relation, this is responsible for the past. So this variable keeps track of the past history of the displacement up to the actual time t. And then if you perform an integration by parts, you end up with this equation here. Here is this mu is the derivative with respect to s of the old kernel change of sign. And you arrive to this equation here, which I'm gonna call from now on our memory equation. And okay, and now, so the variables are u. Well, in fact, since this is a second order in time equation, the variables are u and ut. And then you have this extra variable eta, and which are the spaces, the natural phase space for this variable. Now, u and ut are in H01 because we took the Rheological boundary condition, and L2. And oops, made a mistake, sorry. And eta lives in this space, which I called MT. This is a space of function from R plus with values into a geometric space, which in this case is H01, but with respect to the measure mu t of S ds. So the problem is that at the phase space of your problem, of our problem, depends itself explicitly on time. And this requires somehow new methods, and one paper that at least as far as I know, first addressed question of this time is a paper of Diplinio, Duan, and Temam, appeared in 2011. Where they developed a theory of processes acting on time-dependent spaces. So the first, the first step is to establish a well-posedness result. And as I was saying, the time-dependent kernel in fact creates some problems. So to better understand why we have some problems, let's see what happens in the, let's say, classical, in the sense previously studied case of a kernel which does not depend explicitly on time. So if you have a kernel which does not depend on time, then the third component of the space, which is usually called the history space, it is just an L2 space with a fixed measure. And formally, if you consider, so let me just go back. Okay, consider this variable here. If you take derivative with respect to t and respect to s, what you get a supplementary differential equation. In fact, you needed another differential equation, otherwise you could not solve your system. And this is a differential equation on M. Now, this is minus the derivative with respect to the internal variable S. Upon constructing the correct functional setting, this guy here is nothing but the infinitesimal generator of the right translation semigroup on this space here. And the miles, assuming that u of t is known, and so this is, let's say, an external source, the solution to this equation can be written explicitly, and it has this, let's say, representation formula where eta tau and u tau are initial time, which are assigned at an initial time tau. And okay. Now, one way to get estimates is to multiply this equation by eta t in the space M, and these and this in order to produce energy estimates. And the key point is this equality here, that if you multiply the derivative in time of eta t times eta t in m, you get this, you get 1/2 of the time derivative of the square norm. But since we are working in a time-dependent space, the first problem is in the very definition of the derivative, because you see, when time changes, your object is in a different space. And so it's even difficult to think to the definition of the derivative. Of course, you can define somehow right or left derivatives if your spaces, let's say, either shrink or they blow. But in general, you have no way to define the derivative. And well, oops, what happened? Do you see it correctly? Because
no, we
it is small, right?
Very small, yeah. I think maybe you, I don't know, maybe
okay,
zoom out without.
Okay, no. Okay.
Okay.
No, it's fine.
Now it's fine.
Okay, now it is. Okay, as I was saying, to overcome this obstacle, the idea is to propose a different notion of solution, and namely is to say that U eta solves the problem if the equation M, the memory equation, which I wrote here, holds in the weak sense, and we postulate the evolution of eta by saying that eta satisfies this formula. And it's quite interestingly, I would like to mention that this alternative definition is can also be used in the classical scheme, and it is actually equivalent, but it is more useful aiming to study, for instance, when you want to prove uniqueness for equation of this kind, uniqueness is a real pain in the neck. But if you use this notion of solution, you can simplify the arguments a lot. Okay, so what is then our strategy? The problem is that we do not have this differential equality. And even if we assume that in some way we can define this derivative, then what we have formally is this guy here. But what we want is to take out the time derivative. And this is something that at this level we cannot possibly do, because we don't have any regularity here. I mean, we are very far from having the required regularity to do something like that. So what we have to do, we have to make some painful approximation, and at the end of the story, to derive integral inequalities. And this is exactly what we did. And so the result is that under quite general conditions on the kernel, we could prove a well-Poisson's result, and then also a continuous dependence estimates. And namely, in other words, for every initial datum that I call Z tau belonging to the space H tau, so at time tau, we can write the solution at time t as U of t tau applied to Z tau. And this guy U t tau is a two-family of operators that maps the space HT into H tau into HT. And this is what we call, well, not me, but the first one who studied these objects, they call this a process on time-dependent spaces. And so let me briefly go to the long time behavior. Now, concerning the long time behavior, once we have the existence and uniqueness, we need to make an extra assumption. And the assumption is written here. The dot is the derivative with respect to time, and the prime the derivative with respect to S. And well, one might be surprised by an inequality of this kind, but see, if mu is time independent and say of unit mass, this inequality boils down to this inequality here. And this assumption is used with no exceptions by everybody in connection with equation of this kind. So there are at least 100 papers that I know where this assumption is made. And this key assumption is generally satisfied, I have to say, and in particular, it is satisfied by the Rheological kernel that we considered before. And well, the first result that I can state is a dissipative estimate of this kind. So if you consider the energy at time t with initial data given at time tau, which is nothing but the, of course, this depends on the initial datum that you choose, okay? What we prove is that there exists a universal constant omega and R0, and so that the energy is controlled by Q of R. This is an increasing function. R is the size, let's say, of the initial datum, times a negative exponential of the difference time minus tau plus this R0. So this R0 basically is the radius of the absorbing set, so to speak. And I would like to mention that this estimate is quite interesting because it's two-sided. So you get close to R0 if the difference t minus tau goes to plus infinity. This means that this can be reached either by letting tau go to minus infinity or by letting t go to plus infinity. And well, this result is new also for the case of time-dependent kernels, by the way. And once we have this estimate, we can prove the existence of a time-dependent global attractor. Time-dependent global attractor is a family labeled by T, which has satisfied certain properties. So each, we call an element AT of the family a section. So each element AT is compact in his relative space HT. We have the invariance property, which is expressed by this last equality here. And we have an attraction property, but you see, and this is really the one drawback of this theory, this attraction property is of a pullback type. Here, from my point of view, it would be very interesting to produce a result on the existence of forward attractors, but at the moment this seems really out of reach. And so, as I was saying, the result is that we do prove the existence of the global attractor, and the attractor has the best optimal possible regularity. But what I was more interested in is to go back and discuss the limit when our kernel converges in some distributional sense to the Dirac mass at 0. And so, as I was saying, in the long time, the problem formally collapses into the Kelvin-Voigt model. And what we would like to do is to render this assertion somehow rigorous. And the Kelvin-Voigt equation generates a strongly continuous semigroup, and these semigroup has a classical global attractor, which I call the infinity. This is a very old paper of Roger Temam and Guidaglia. And what we prove is a closeness. Of course, the space of the strongly damped wave equation contains just the first two components of our space. And so what we have to do is to, let's say, project our attractor on the first two components. So we have to use this canonical projection. And when GT goes to the Dirac mass at 0, what we have the convergence of the projection of AT to the attractor A infinity, and this convergence is given in terms of Hausdorff semi-distance. Okay, so these are the references of these two papers. And thank you very much for your kind attention.
Thank you very much. And okay, we have time for a few questions. Is there any question or comment? Okay, maybe I have one. When you consider the long-term behavior, you have this this assumption, so you call it the key assumption. Do you have an interpretation for that? You said that in
yes.
Short memory is.
Let's say, let me speak about this, because this is simpler.
Mm-hmm.
Okay, this assumption basically, and consider even a simpler situation where you do not have nonlinearity. So just consider the linear model. Now, the linear model is simple. It generates a strongly continuous semigroup. And from the general theory of C0 semigroups, what can happen is that either the semigroup norm has a uniform decay, and if the decay is uniform by the semigroup properties, it turns out to be exponential,
mm-hmm.
or you do not decay at all. So if the norm goes, let's say, in this particular case, also these are contraction semigroups. So the norm is always less than or equal to 1. So either the norm is equal to 1 or it goes below 1. And if it goes below 1, then you have exponential decay. Now, in order to have exponential decay, it is necessary that the kernel, the memory kernel, has an exponential decay. Otherwise, there is no hope to have an exponential decay. But this relation is, in fact, this is only sufficient. This is not the best that you can find in the classical situation. But basically, if you want to have a good long time behavior, for the linear case, you need to have a kernel which behaves well and it has a strong decay. Otherwise, your system will not decay. And of course, in the linear case, the attractor is trivial; it's just 1 point. Okay, but nothing changes if you add a nonlinearity. If you don't have absorbing set, then you don't have attractors. And in order to have absorbing set, you need a decay of the kernel of this time. Here, okay, the situation is, is a little bit more complicated.
Sure.
Now I lost okay, it's a little bit more complicated because basically you need to have a formula of this kind for each t fixed, but then you also have the dependence on t, which should not destroy the pattern too much.
Okay, thank you.